propositional setting. There's the bulk of proof complexity happening, but and the main objective of proof complexity is really to understand the size of proof. So you're given a formal proof system, and the main complexity measure you're trying to understand is how long do proofs need to be. So similar to the analysis of algorithms, where you're mainly interested in running time, proof size is here the main thing. And as I was saying, main framework has always been propositional logic. We want to do this slightly differently and look at quantification. Why is QBF interesting? Well, first, I would argue that quantification is really a very natural phenomenon occurring in logic. So likewise in propositional logic. This has been an ongoing work over the last 15 years or so, and I think there's a very interesting theory emerging. What I also find interesting, and this is one theme I want to highlight during this talk, is that we will see different effects from propositional proof complexity. So it's not just the replication of facts that of things that has happened in the propositional world, but new things pop up and shed different light also on why or why not things work in the propositional setting. And in the last part, I'll try to explain how this is intimately related to efficient solving, so QBF solving powerful algorithms for this P-space complete problem. Now, just maybe a few words on that. So how does this relate to solving? Different resolution systems have been designed that capture ideas in solving. There are different algorithmic paradigms, CDCL, which you might know from SAT solving, but also different approaches, expanding universal variables, for instance, dependency schemes. And proof complexity can prove the soundness of these approaches and also identify weaknesses and identify areas of improvements by showing lower bounds. It's also a very interesting case in terms of where the complexity lies. So where you see you've got basically a timeline here. Breakthrough in the late 90s. We are at an earlier stage, but we are at industrial applicability now. And then if you move even higher, NX time complete DQBF, dependency QBFs, which is an early stage, but also lots of stuff happening at the moment. Now, just to see what's our framework, we work with quantified Boolean formulas. And a QBF is, in our scenario, is a fully quantified Boolean formula. You've got a quantifier prefix, and then you've got the matrix, which in our case is in conjunctive normal form, is a CNF matrix. Now, if all variables are quantified in the prefix, then these QBFs must be either true or false. And this is exactly the problem we want to understand and want to solve, and that's the P-space complete problem. And in accordance with what's happening in propositional proof complexity, we are mainly considering refutation calculi for false QBF. So we are given a false QBF, and we want to prove that this QBF is indeed false. And as I said before, the main object of study is how succinct these proofs can be or cannot be. Now, semantically, you're probably familiar with the view that you can see these QBFs as a two-player game between an existential and a universal player. They just follow the prefix and set the variables to either 0 or 1 in the respective order. And then the universal player wins if you falsify a clause, and otherwise, if all the clauses get satisfied, the existential player wins. Now, if you look at it as a very simple example, you've got this QBF here. Obviously, the existential player starts by choosing x. Let's say he sets x equal 1. Then you will simplify the formula. So this clause gets simplified, this clause gets satisfied, and we are left with this remaining CNF. Now the universal needs to respond and say he plays u equal 1. You see that this simplifies the formula further, and you are left with t and not t. And now whatever the existential player does, he inevitably loses this thing. So he lost this game, but moreover, this formula can easily be seen to be false, so the universal has a winning strategy no matter what the existential was doing. The universal player, that's That's very much an Herbrang function, so the opposite of what Supratik was just, the dual concept of what Supratik was just talking about in his talk on scholarmization. Now, if you want to understand proof complexity, then we need some proof systems, some calculi for a start. And propositional resolution has been the best studied system. So what do we have as an analog here? It is called QU resolution, or maybe let's just call it QBF resolution for this talk. We've got the well-known resolution rule. You've got two clauses which you can resolve on conflicting existential variable. You have X or not X. You derive this new clause. This is as you might know it from propositional. But now we have one more rule which is called universal reduction. And this allows, if you have a clause which has a universal variable in it, U, and U is universally quantified, such that C does not contain variables right of U in the quantifier prefix. So in other words, nothing in this clause C or U depends really on U at the point when the universal player is asked for his choice for U, all the variables in C have been set already, then you might as well say you can drop the U. Because in this semantical view, if you have a way how to satisfy, how to win on C or U for the universal player, yeah, you better have a way how to win on C, because I mean everything is determined before you actually come to U. Yeah. Okay, so this is a rule. If we have a refutational calculus, let's just look at a very simple example. Suppose this is your formula. You can make a step on X, resolve, you get a unit clause U, and now you use universal reduction. Obviously here nothing depends on U in this clause, and you get the empty clause, thereby demonstrating that the formula is false.
What we are proving that the universal
formula is false that we are given. Yes, thank you. Now it turns out that you make this more general. You can start with any propositional proof system, call it P, and it operates with some lines. These may be clauses, these may be inequalities, these may be formulas. Let's say we are working with formulas here. You have F, X, U, and this is a propositional line in your refutation. You use the rules that you have in your propositional system as we did before with resolution, and you add this one universal reduction rule. You have the same condition that nothing in this formula fxu should depend on u, and then you're allowed to substitute u equals 0 or u equal 1 into the formula as you wish. And then it is not difficult to verify that if you start with any natural line-based propositional proof system where you have lines consisting of formulas or whatever, you define the proof system Q by adding this universal reduction rule, and you get a sound and complete proof system for QBF. And if you remember what we did for resolution on the last slide, we started with propositional resolution, we added this universal reduction rule, which is exactly the same rule as here. Yeah, because if you look back, here we just said we could drop the u, and this means you'd set u to 0 in that case. Yeah. So it's exactly a generalization of that rule, which is sufficient to give you a sound and complete QBF proof system. And I mean, there are many more QBF proof systems studied in the literature, more powerful ones, weaker ones, but these are the ones that we want to mainly focus here. And perhaps a very interesting case in point are Frege systems, called Frege. In logic communities, first order proving they are typically referred to as Hilbert type systems. So they just use a collection of axiom schemes, rules, for instance, modus ponens. And for propositional logic, it's important how you represent the lines. Very often we do this by circuits. So when we speak of C Frege, where C is some circuit class restricting the formulas allowed in the system. So you can, for instance, look at formulas of bounded depths. You get to AC0 Frege. You allow mod P gates. You have AC0 mod P Frege. You allow counting. Then you have TC0 Frege. The usual circuit class kind of parameterization can be done here. And here you have an overview of the well, of some of the most important propositional proof systems which have been studied propositionally. Here is resolution that I mentioned. Here is AC0 Frege systems, extensions thereof, weaker systems of resolution, tree resolution, for instance, where the proofs need to be tree-like. On the other side, you have algebraic systems. There are many of these systems. The red line indicates the current research line for which systems do we have lower bounds. These are all exponential lower bounds, whereas for the systems above, in particular for Frege, this is wide open. We don't have any lower bounds whatsoever. It's a major question of research. And by doing this transformation, adding this universal reduction rule, all these systems, most of them at least, all the dynamic ones, can be turned into QBF proof systems in really one shot. So we've got the same kind of structure here, which we want to understand what's going on. And we want to see how we can analyze proof size there and what's possibly different. So is this just a replication of this picture and we quantify and there's nothing new, or what does happen? That's what I'm trying to understand and answer in the first part of this talk. And then I said this is a survey. So when we started this research, well, a bit more than 10 years ago, we actually thought, okay, so what's the most obvious thing? We look at the techniques that we've got in propositional logic and propositional proof complexity. And there the situation is actually quite good, that we do know a couple of techniques. Feasible interpolation is one of the successful techniques for resolution, for cutting planes. There's a size-width relation, which is probably the most often used technique to show lower bounds, particularly for resolution. There are game theoretic techniques. There are also more complex things, proof complexity generators. And we kind of started off our research by trying to understand what works in QBF. I mean, there's also a close connection or postulated connection to circuit complexity, which I will mention more of later. And in our first results, we really looked at, okay, feasible interpolation, yes, we can transfer that mechanism. It works in QBF. Size-width relation, okay, we showed it doesn't work. We have concrete counterexamples. Game theoretic techniques, we showed they do work. Game becomes more complicated. Analysis is also somewhat more involved, but it works. This is kind of how we started. And I mean, it's a very natural start to make. But in retrospect, in hindsight, somehow now we are a bit further ahead. We really understand better of what's going on. And this is not exactly the main point that we observed in these early works. The central lower bound technique, the central thing to understand in QBF is really a technique called strategy extraction. Strategy extraction means you start from a proof. Remember that we only consider false QBFs. You start from a proof, and now you know the formula is false, and you've got a proof for that. And from the proof, you want to extract the winning strategy for the universal player, which you know must exist, but you want to extract it in some computational format. Yeah, so from the proof, you want to extract. This is actually quite related to the problem that Supratik was talking about. He wants to construct Skolem functions. We want to extract these Herban functions in our case. And how this can be useful for lower bounds is, if you just use the intuition, if the winning strategy is complex in some sense, could be computational complex, or we also see other things, then proofs will have to be long because we have these strategy extraction efficiently.
Any winning strategy must be
Correct. Yes. Yes.
that could be multiple.
Yeah, of course, yeah. But if you start with a short proof, then you will be able to extract a short winning strategy. If there isn't any short winning strategy, there isn't any short proof. That's the logic. Right, and then it turns out that actually feasible interpolation, this technique I mentioned previously, is a special case of strategy extraction. And we also found out that size-width, which you ruled out before, works as a kind of corollary to strategy extraction. But there is a different formulation here. So the formula becomes different. The size-width transfer works, but the actual formulation is different. And I mean, so the counterexamples that we had before when we said it fails, these are correct, but still it's not the right message somehow. I should make one remark that in QBF proof complexity, since we started to transfer all our systems from the propositional domain, you get very easy and cheap hardness for free by a simple trick. Namely, if you start with any formula phi, which is propositionally hard for system P, then you just quantify it existentially, and this will be hard for my QBF system. Because there aren't any universal quantifiers, universal reduction is never useful, so it just collapses to the propositional thing, and there's nothing new. And this is not necessarily what we are interested in. So we kind of want to discount this sort of hardness. So what we could do is, just count the number of universal reduction steps, which perhaps looks a bit artificial as a measure, but you can also model it more elegantly by allowing an NP oracle that filters away all the propositional derivations, all the propositional hardness. It's actually quite typical that we use NP oracles in QBF proof complexity and also in QBF solving, I should rather say. So this is actually a very natural thing to do. You can model it formally by saying if you have got any propositional semantically valid step, you can do it in one step with this NP system, and we call this then NP oracle adding to the QBF system, but maybe we don't need to precisely define it here. So just as an intuition, suffices to understand that with using these NP oracles in QBF proof systems, we eliminate all this propositional hardness. And now the main question that we are interested in, what is left? Is there anything that's hard here, and for what reason? And it turns out that the answer can be very succinctly given by circuit complexity is the answer here. Circuit complexity lower bounds are those that make QBF proofs complex. Yeah? And this is a very nice connection, which is a very general one. So in circuit complexity, you might remember all the talks yesterday. The message was quite clearly, whether it's in algebraic circuits or Boolean circuits, circuit lower bounds very, very hard. So immensely complex problem, and one of the hardest, oldest problems in that field. Now, same you have in proof complexity. You want to show systems, particularly these Frege systems I mentioned, same open problem. Then turns question whether these problems are somehow connected. And there is actually in proof complexity a long tradition of postulating such a connection. I've got here a quote from a survey of Paul Beam and Tony Pitassi some 20 years ago. And they say that this general correspondence between circuit classes and proof systems, and then they go on and say that this intuition for this approach is that any tautology that needs to use in its proof some concept that is not representable in complexity class C will not be efficiently provable in C Frege. So let me translate this maybe a bit simpler words. There's this general belief that connections between lower bounds for proof systems working with C circuits, so where the lines are objects from complexity class C, and lower bounds for that very same complexity class C are somehow related. So for instance, if you have extended Frege, you're working with lines that are Boolean circuits, and now the intuition is that lower bounds for proof size for extended Frege somehow have to do with lower bounds Boolean circuits for unrestricted Boolean circuits. Yeah, so this is the example I've got here. Are lower bounds for P/poly somehow related to lower bounds for extended Frege? You can ask the same questions for all the other things. AC0 mod P Frege lower bounds, are they somehow useful for AC0 mod P Frege systems? And this is not known. This has been conjectured for a long time, but couldn't have been made formal yet. There are some, connections, in particular, interpolation is a connection between circuits and formulas and proof size, but it's not as direct as we wish for in this thing. Now what turns out is that in QF, we can actually characterize this very precisely and succinctly. Namely, if we start with any of these Q Frege systems, so Q is just Frege, then we can show that there exist hard formulas for this system if and only if there exist lower bounds for propositional Frege, major open problem 1, or there exist lower bounds for non-uniform NC1, major open problem in a circuit complexity. So the precise condition would be P space, it's not contained in non-uniform NC1. Or alternatively, if you use this NP oracle in the system, so if you want to eliminate the propositional hardness, which is here still present in case 1, I mean, it's non-trivial propositional hardness in case of Frege, but anyway, if you want to get rid of this, you can say that a super polynomial lower bound in this QBF Frege system with an NP oracle is exactly the same as showing a lower bound for a non-uniform NC1. And if you move to extended Frege, it's exactly, which is even more powerful, it's exactly equivalent to showing a lower bound for P/poly. I mean, for a problem that needs to be in P space, because otherwise we can't express it as a QBF. And this works for all the usual Frege systems that you can think of, parameterized by all these classes. So just maybe a few remarks on how this would work. What you
Which one of them?
all of them.
Oh.
Yeah.
Like the papers that prove these things, do they use one specific strategy or multiple?
So the kind of statement is that if you have a circuit class C, then C Frege lower bound with an NP oracle is equivalent to a C lower bound on that circuit class C. And you can parameterize C by any of these classes. Yeah?
So we know that each space is not AC0 mod P, so you get lower bound.
Exactly, very good point. Yes, that's I'm coming to that in 2 slides. Yeah, thank you. So how can we do this actually? So we somehow need to translate these circuit lower bounds into QBF, and one easy mechanism, I mean there could be different ways how to do it, but one really simple way is you start with a Boolean function, say f, for which you might know a lower bound, and now you construct a QBF, which I call QF, and this QF formula is simply saying I've got an input x, so x is a bunch of existential variables, and I want to evaluate f of x, and I want to say this is different from z, and z is universally quantified. I need some auxiliary variables t, which describe the computation of a circuit for f. So I assume that f maybe is given succinctly as a Boolean circuit. I can express this as a QBF. This is a QBF. And now you just need to see what's the universal. So this QBF is false because it's simply saying that the function f isn't total. There is an x such that the output of f of x is neither 0 or 1. But the crucial thing is what the universal player needs to do to win is to make this matrix false, and you only make it false by playing z equal f of x. So the only winning strategy needs to compute f. But f is the Boolean function we started with, and that was a hard function. So then what we can say, now you see exactly how this works. So this is exactly the answer to your question. So you start with the AC0 mod P lower bound, famous lower bound from the 80s, and you use so this is a lower bound for parity. You take the Q parity formulas as defined on the last slide, and these will be hard for AC0 mod P QBF Frege systems. Yeah, particularly they are also hard for Q resolution, but they are even hard for AC0 mod P Frege. And in contrast, such a lower bound is not known propositionally, even though we of course have this lower bound for AC0 mod P Frege. Yeah. Sorry, say again? No, T is like a bunch of Zeithin variables. These are helper variables. You need to encode the circuit, and they No, he needs to set them correctly, otherwise he will lose. Otherwise the existential player, yeah, okay. Right. Okay, so you can see, I mean, this is the hierarchy of Frege systems that I mentioned before. And you see that, I mean, the research line is somewhat different in QBF than from propositional. In QBF, we can use all the circuit bounds that we have in the literature, and in propositional, we didn't yet understand how to do this for AC0 mod P Frege. Now, it's interesting perhaps to look at what happens for resolution exactly. Because resolution is not neatly characterized as a Frege system in this hierarchy, but on the other hand, resolution is the most interesting case also in terms of applications, because QBF solving is modeled by resolution system. I'll say a bit on that later on. The answer is that for resolution, we can also tightly characterize it, but by a model which is based on decision lists, by decision list model. And as a byproduct, we get the size-width relation, which I alluded to previously. So what's this circuit model? This decision list model is very simple. So decision list looks like this. You compute a Boolean function. Say it's a Boolean function in input variables x and output variables u. And then you have conditions, which in our case are just terms, so conjunctions of literals in the existentials. The t's are terms in x. And you evaluate these. And if a term becomes true, so if one of these lines fires, then you just give the corresponding answer. So you just say that u has exactly these values and the b's are just total Boolean assignments. So it's a very easy computational model. You just go one by line and you check if the condition is true. If so, you give the corresponding output. We call this a unified decision list because it gives an answer. That's the unification. It's an answer for all the universal variables in just one go. It's a way, again, how to extract Herbrang functions, how to compute Herbrang functions. And turns out that this is exactly what to compute winning strategies for QBF resolution. So if phi is a false QBF, we need bounded quantifier complexity, then the size of the smallest Q resolution proofs, again with this NP-Oracle, is polynomially related to the smallest decision list for phi. So the smallest decision list computing a counter model for phi. Again, something is hard for Q resolution if it requires large UDLs or there is some propositional resolution hardness involved. You can also get the size-width relation, which I mentioned before. Here on this slide, I've displayed the classic size-width relation, which you might know from propositional logic due to Benzer-Song-Wigdersen. It's a low, I mean, once you have a lower bound for widths, which is the size of resolution clauses, you can infer a lower bound for size. That's mainly how it is used. It's the predominant technique for showing size lower bounds in a propositional world. First, we saw this one doesn't work, and exactly this formula does not work. But you see, we get a very similar looking formula, although not identical. If you look at the details, I mean, there's most crucially perhaps there's the quantification depth entering the formula. D is the quantifier alternation, and this is simply a byproduct from this UDL characterization because we can prove a very analogous size-width lower bound to Benzer-Song's Wigdersen result for UDLs. Anyway, let's use it for some concrete lower bounds. So we've seen this parity formula before, which we already know is hard for Q resolution, but for which we use the circuit complexity lower bound. We use the AC0 mod P lower bound for parity. Now somehow that's really that's really an overkill, because we use this strong lower bound from circuit complexity to prove a really simple lower bound for resolution. We can prove it much more directly, much more easily. So this is the formula that I've shown to you before. I mean, spelled out a bit with all the t variables correctly plugged in. Single winning strategy is still to compute a parity. And now it's easy to see that if you have a UDL which computes, so the UDL needs to compute the value for u. So it's a bunch of if, then, else conditions on the u variables. So it's easy to see that the output for the first line needs to be a correct parity of some x's. So you better know all the x's, otherwise you can't compute a parity. So the first line needs to contain all the x's, and therefore the width of that UDL is large. By size width, which I had on the last slide, you get immediately an exponential lower bound. So we don't really need to use this strong machinery from circuit complexity to show innocent lower bounds for QBF resolution. Yeah. Second example are equality formulas. So it's a very simple formula saying you've got a bunch of x variables, now the same number of u variables, and you want to enforce that the only winning strategy is to compute ui equal xi, so to replicate the existential choices. That's what you want. That's the only winning strategy. If you look at this formula, it's very easy to see that exactly realized in this formula, in this matrix. Yeah, the t are again some helper variables to make that work. And these formulas can also be easily shown to be hard by the same method, or actually by using a different method, which I want to explain now, which is called size, cost, capacity. So this is a technique which is again very unique to the QBF world, and it's a very semantic technique, which I think is quite nice, and I want to illustrate a new application of that technique in the following, which is why I want to. So we are again in the strategy extraction problem. We fix the winning strategy S for QBF phi. And now as a complexity measure for that winning strategy, we don't look at the computational cost to compute it, but we simply look at the size of all the answers. So as a function, we look at the size of the range. So then we say the cost of phi is the minimum of this range size over all winning strategies. So we look at all winning strategies, and we are interested in the one winning strategy where the universal player has the least number of responses to make, has to give only few answers. So we are not, before we were looking, is the winning strategy complex to compute in some circuit model? Now we look at a much simpler question and simply want to understand how many answers does the universal player need to give to win against that existential player. Yeah, and the idea is that if you have only strategies that require many responses for the universal players, these are costly, and these will kind of correspond to many lines in your UDL, and hence make the proof large. So again, look at the equality formulas that you had seen before. The only winning strategy for these for these formulas, as we know, is for the universal player to play ui equal xi, and that means, I mean, since there are 2 to the n existential challenges, I mean, there are 2 to the n ways to set the x variables. The universal needs to, in the only winning strategy, needs to reply with exactly the same 2 to the n answers. I mean, there's nothing else he can do. He needs to only replicate x variables, so the cost is clearly exponential. I was mentioning a technique is called size, cost, capacity. So capacity is another measure which I don't want to explain precisely, but it's roughly the number of responses that you need to make per proof line. So what do I mean by this? If I have a clause, then I just need to make one response, whatever the situation is. So look, for instance, at this situation here. I've got the existential x and the universal u, and the universal doesn't really need to know what the existential was playing, whether he plays x equal 1 or x equal 0 is really immaterial to him. It would be always the best answer to say u is equal to 0, because he wants to make the thing false. Yeah. So playing u equal 1 doesn't really make sense in that scenario. So it's only reasonable for him to play u equal 0. So therefore, resolution has capacity 1. And now we showed a very semantic lower bound for proof size. Namely, if you have any proof system QP, even with an NP oracle, then the proof size pi for some formula phi is the cost of phi divided by the capacity of the proof. Now in resolution, this boils down to something very simple. We know, for instance, for the equality formula, let's just look at this example. Equality formulas, we've just computed the cost is exponential, the capacity is 1, so the proof size is exactly exponential. That's what we can infer. And this is simply by looking at the equality formulas and realizing that you need to give exponentially many answers for the universal player. Right. So maybe an intuition on why this is true. You know that you have a strategy extraction algorithm, and the strategy extraction algorithm needs to kind of extract all these responses from the proof. Now, the cost counts the number of necessary responses, and the capacity somehow gives an upper bound on how many responses can be extracted from one single line of the proof. So thereby, if you have to extract so many responses, and from one line you can only get one response, you need that many lines in the proof. That's somehow the intuition of why this is true. Yeah? This is for strategies in general, but in particular you can think about UDLs, and if you think about UDLs, then you see that one response is exactly one output, one line in the UDL. Yeah, but this is, this simply talks about proof size in resolution, for instance, or proof size in cutting planes. Works the same for cutting planes, where you have different UDLs. Okay. So, and what is quite nice is that this is a lower bound technique with a very semantic flavor. Works for all base systems and always produces these genuine QBF lower bounds where you can plug in an NP oracle to your proof system. And now I want to illustrate this on some formulas, and this is actually pretty recent research, which is going to appear in AAAI next year. But let me explain a bit of context. So if we start from any co-NP complete problem, let's maybe move to the propositional world to make the point. So if we start from any co-NP complete problem, and if we assume that NP is not equal to co-NP, which I'm sure we all believe, then translating this co-NP problem into propositional formulas, into propositional logic, will manifest in hard formulas. So why is this? Because guessing proofs, if there were easy proofs in some system, you could simply guess them in NP, and that would show that NP is equal co-NP because we're starting with a co-NP complete problem. So for instance, let's illustrate this on the clique formulas. So the clique formulas naturally express that a given graph does not contain a k-clique. Yeah? Can easily express that in propositional logic. And now assuming that NP is different from co-NP, all these formulas need to be hard for any propositional proof system, even for Frege, for which you do not have any lower bound. But assuming NP is different from co-NP, these formulas will be hard. And the challenge somehow that we are looking at is to show this unconditionally. We would like to show that this is true regardless of making computational complexity assumptions. And there's an actually quite interesting line of research. So some more than 10 years back, we looked at this, we defined these formulas and we looked at this in tree-like resolution. We actually wanted to show something more, that this works for resolution, but then we realized, okay, it's not so easy. We started tree-like resolution and then we had a lower bound for this. And then this was picked up by quite a number of people, and it turned out to be a really hard problem. And in the breakthrough result a few years back, it was shown to be hard for regular resolution, particularly by Jakob and Susanna here, who are also here. And the case for resolution is still a major open problem in proof complexity. We know it's true, it must be true, but we are not able to prove it. And what I want to show to you now is that this actually works very nicely in QBF. It's again a difference how things pan out in these different worlds. So what's the analogous version here? We start from any problem which is hard for some level of the polynomial hierarchy, and we formulate this as a QBF. It's very natural. That's always what you do, in terms of applications. You have a problem hard for sigma 2, 3, 2, or whatever. You formulate this as a QBF. And again, assuming that polynomial hierarchy doesn't collapse to NP, these QBFs must be hard for every propositional QBF proof system. So it's again the same kind of assumption. Yeah? And we want as before in the propositional world with the click formulas, we want to show this unconditionally. We want to show that these are hard unconditionally for resolution's sake. And now the thing is, the nice thing is, we can actually do this. We can show it, and it's actually quite simple. We use this size cost capacity theorem. We use our semantic characterization for lower bounds that I explained to you a few slides back. And we illustrated this on some sample problems, which, as I mentioned, is work that's upcoming in conference next year. So the work is actually quite simple. You start with a computationally hard problem, which is asking, I mean, whether some property holds for some structure. Yeah. You can translate this into QBF. This is standard because it's a problem from the polynomial hierarchy somewhere. And now on the other hand, we need some family, and this is where a bit of work is involved. We need some family, which we call a critical family. So we need a family of structures such that it only just fails to have property P. So remember, we want to have a formula which is false. So we are looking here at some instances where the answer is no, where the structure doesn't have the property P. So for instance, the graph doesn't have a click. Yeah. So we're looking at these things. And now we want to understand the critical family would be a family of graphs where it has clicks, but I mean just very few ones and only just fails to have the no property. And then we show that these will result in F families. I'll make that a bit more illustrative on one particular example. So the example is a k-radius problem. So you're given a graph and you are asking whether the graph has a k-radius. So for instance, in this graph, if you fix k equals 3, then f would be a 3 center because you can reach any node from f in 3 steps. Yeah. This 8, so for instance, BC this has a path of length 3, and you have got that for any node here. So this has a 3 center. And in order to make this an interesting problem, I mean, you see that you can actually compute centers very efficiently. It's not a hard problem at all. But in order to turn this into a hard problem, we need to represent the graph succinctly. So this can be done in a model due to Galperin and Victorson. You have a direct graph G, and you have a circuit which computes the edge relation. So you have a circuit C with 2n input gates, and C with xy computes 1 if and only if xy is an edge. Yeah. So this is an implicit representation of the circuit. And of course, you can imagine that this represents many graphs exponentially more succinct than giving them, I mean, explicitly with an adjacency matrix, for instance. This is important because otherwise the problem isn't even hard. But it's in succinct representation. Hemmers, Pandra, Tantau, Watanabe were showing that this is a sigma 3p complete problem. And now what we show is that this problem gives rise to hard formulas in QBF resolution, for instance. Yeah. So it's the analogous version of what we were trying to do with the click formula. We know it's a co-NP complete problem not to have a click and try to show that this is hard for resolution. Here we start with a sigma 3 problem, in this case this radius problem, and show that this is exponentially hard for QBF resolution. And how does this work? It's actually quite simple. So you just need to construct graphs with particular properties. So we start with some graphs. I mean, so the idea is we need to somehow make the universal player work hard on his winning strategy, give many responses for his winning strategy. So here the idea is that these V1s, vertices in the first column, they are potential K-centers. Yeah, they are not K-centers because these vertices in the last column, they are not reachable in K steps. All the other vertices are reachable in K steps. And now we make the formula that even are reachable in K steps, most of them, except one vertex. So for instance, if the existential player is saying, well, this is, okay, so we need to say how the QBF formulation looks like in the first place. It's very natural. The QBF formulation is simply, the existential player is saying, I've got here my vertex, which is the K center, and the universal player needs to say, well, here's a vertex which is not K reachable. And if he can do this, then he demonstrates that there is no K center. So what's the existential doing here in this game? He is saying, for instance, V1 is my K center. And you can look at this graph, so you can reach all other vertices in K steps except this one. This is the only vertex you can't reach in K steps. So then the universal player needs to answer with this one. Yeah? This is his unique answer. And now the existential can say, okay, so what if this is my K center? Again, he has a unique answer here, this one. And you see, you can do this for all the n vertices, and you force the universal player to go through all the vertices on the other side. So what is the cost of this strategy, or of any strategy? It's at least n. Yeah, at least n. Now this itself is not good enough, but because we have the succinct representation, this is exponential in our input size. Input size was just log n, because it's easy to see that these graphs can be succinctly represented in logarithmic size, logarithmic circles. Cost is n, therefore the QBFs require exponential size proofs. Yeah, and this is shown completely, generic. The nice thing is that typically in proof complexity, when you show lower bounds, you really need to work with the formulas quite a bit. You need to look at the formulas as the syntactic structure, and you kind of try to prove some invariance. You don't do this here at all. I just described very semantically how you define the formula. The formula might be actually quite messy because it needs to it needs to talk about this circuit that's actually outputting the graph. So the formula will look ugly, and it will not be nice to do proof complexity for these formulas. But we don't need to look at the syntactic details of the formula. We just need to understand this semantic lower bound measure. We just need to compute the cost. And this is very simple because we can simply argue with these graphs that I had here. Yeah? Okay. So, and this we claim is a much more general approach. So we don't have a meter theorem here, but we looked at some other problems from graph theory, from logic, at games. And it's always a bit of an individual case study. You need to find these critical families, but otherwise, I'm fairly confident that this is like a general method how to do that. I'm not quite sure how I'm doing on time. How much? 10 minutes left? Oh, excellent. Thank you. Well, now I want to come to something completely different. So in the beginning, I mentioned that I want to talk a bit on relations to QBF solving as well. So let me start by a reference, The Tale of Two Cities. You might sound familiar. So what are the two cities here? Two different viewpoints on SAT. So the one is SAT is hard. That's the computational complexity message that has been coming to us, since the 70s, 80s, and then the other one coming from SAT solving, which is saying, well, SAT is very easy. It's routinely solved for many industrial problems for big formulas and millions of variables, and it has, applications all over the place. So from a theoretical point of view, you really want to understand what's going on here. Why are these SAT solvers so successful, but also where are the limitations? Because there need to be limitations as P is equal to NP. Looking a bit back into the history, SAT solving started in the 60s by an easy algorithm due to Davis and Putnam, or DPLL as it's usually called. You choose variables X, and then you simplify the formula, and you do this until you either find a satisfying assignment or you somehow exhaustively search. Yeah, you can do some shortcuts, but basically this is the idea. And this didn't work for quite some time. And the breakthrough in SAT solving happened in the late 90s when a concept called clause learning was developed. And it was realized that by doing clause learning plus a number of other things like restarts, choosing good decision strategies, I mean, the way how you choose these variables X is, of course, crucial for how the running time evolves. Many different things that came together made this a very, very fruitful approach. Is the dominant approach in SAT solving these days. Called CDCL for conflict-driven clause learning. I've got a CDCL pseudocode here, but I don't want to go into detail. It's just enough to know that this is the most efficient algorithm that we have for SAT solving these days. And I mean, since I'm talking about QBF here, next natural question would be what happens in QBF? And it turns out that this actually also lifts to the QBF level in a paradigm called QCDCL. This was realized some 20 years back. I mean, it's not completely trivial because there are some additional challenges. You have to sort out how unit propagation works exactly, how you do the selection of decision variables. There are different constraints because you've got a quantification order which plays a role and needs to be obeyed in some sense. And that's one of the main approaches to QBF solving. But in contrast to SAT, where CDCL is really the one approach, I mean, whether for good or bad is a different question, but it's really the one approach that dominates the field very much. In QBF, this is different. I mean, there are different solving approaches. There's expansion solving, there are dependency schemes. There's more choice in terms of what general solving technique you want to follow. But the same question applies here that I mentioned earlier. These SAT QBF solvers work amazingly, and why, and we want to understand where not, and we want to understand how we can potentially improve these solvers. So here I've got a picture that one of my students was drawing quite nicely. So how does this have to do with proof complexity? So you have got your SAT QBF solver on one hand, and it produces a solver trace. And assuming that you've started with a false or unsatisfiable formula, and if the answer of this SAT QBF solver is correct, then you know that the formula is really false. So this solver trace somehow is a proof, must be a proof of falsity. And very often, and this happens to be the case for SAT and QBF solvers, this solver trace can be translated, can be mapped precisely to one of the proof systems that we study. Then it turns out that for CDCL, it translates into resolution. I mean, in practice, there are more succinct formats being used, but in principle, it translates to resolution. And for Q, it's to some variant of Q resolution. And yeah, so it's well known, for instance, that DPLL, this classic procedure, corresponds exactly one-to-one to tree-like resolution. It's a very simple correspondence. Known that it's a major result that CDCL and resolution are equivalent. And this is actually quite something remarkable because CDCL is the main SAT solving paradigm and resolution is by far the best studied proof system. And that this connection holds was, I mean, discovered after SAT solvers had been doing very well for quite some time, and after resolution had been studied for 30 years. So this is really something very remarkable. Question is whether the same happens in QBF. And one answer that we found is that actually it's more complex here, this scenario. So QCDCL and the Q resolution system that I showed to you in the very beginning, they turn out to be incomparable. So there is no direct analogon of this equivalence between resolution and CDCL. They turn to be out incomparable, and you have exponential separations in both directions. And formulas that witness these separations I've shown to you already. Namely, it's Q parity in one direction, which, as we know, is hard for Q resolution. But if you look carefully, it turns out to be easy for QCDCL. And equality, well, we also know is hard for Q resolution. and is also hard for QCDCL, but some variants do the other. Okay. Now, is this only bad news? I mean, proof complexity does not capture solving, or what's going on here? But we had a closer look, and we're saying that you can actually choose different policy in QCDCL and get a bunch of different QBF solving algorithms, QCDCL parameterized by different heuristics for how you decide variables, how you unit propagate, and which variables you propagate. And we showed that all these lead to sound and complete algorithms. And here you have QCDCL. This is in our notation using these kind of heuristics. And this was shown to be incomparable to Q resolution, which you have here. But Q resolution is in fact characterized by a variant, by a different algorithm. And now you can do this for all the other variants which we introduced and see that there are many different ways how you can do QCDCL in practice for QBF. And this is, I think, quite an interesting message for practitioners. I mean, so some of the, this is a separation, this is the simulation order, and for most of these lines we have separations. And you see that the variant that's used in practice is actually quite weak. It's down here. So this is quite an interesting message for practitioners, I would say, because I would encourage them to look at some of the more powerful systems and see whether this is not any good for solving. So we actually have been talking to people, and this is, I think, quite interesting interactions. All right, so let me conclude. I think we are, I'm getting out of time. So what I try to show you is that QBF proof complexity has an interesting theory emerging, both on the theoretical side as well as in interaction with this. It shows quite different effects on propositional proof complexity in the close connection to circuit complexity in particular, and in the easy way how you can show that something is hard from that's computationally hard problem, or proof complexity as well, this kind of paradigm. And well, in the last part, I also try to make the case that there's an intimate to QBF solving. Thank you very much.
The results for a fixed number of alternations, 5 alternations that have studied QBF complexity for that.
So for quantifier alternations of fixed complexity. Yeah, so most of the formulas that we do use, they have only limited alternations. For instance, the equality formulas, that's a sigma 3 formula. The parity formula is a sigma 3 formula. So most of the separations happen on a very basic level. There are only very few results for which you really need unbounded quantification. Thank you.